the fracking or all those unconventional oil and gas applications. But still, this is a very diverse group of people, and I kind of want to provide some take-home message today. So I am from Texas A&M, and I'm going to talk about one of my postdocs' work. So let me first start with a little bit of kind of daily example. So this is a 4-year gasoline and crude oil price chart. When I first joined the Texas A&M in 2015, I mean, as you can see, it was really low. I think the oil price was like this. So, and then it gradually kind of built up, and now it's about the right, I think, the price. So, gradually, a lot of oil and gas companies, they're trying to take some risk in investing some monies to the undeveloped part and so on. And I want to claim that basically this dip was motivated by the shale revolution. But what is really the shale gas, or like unconventional, like a gas? So basically, when we say the shale gas, we're talking about the natural gas trapped in rock with very low porosity and permeability. And you can imagine that the permeability of this unconventional reservoir is almost similar to that of like a sidewalk or like granite, like kitchen top on your kitchen. So without proper rock stimulation, it's very difficult to stimulate and basically reach the economically feasible production rate. And basically, these two technologies are the game changer. First one is horizontal drilling. So while in the conventional one, we only had the vertical drilling, but because of the nature of the shale gas or the tight gas, we start using the horizontal drilling, which is nothing but the drill bit is made to turn from the vertical to the horizontal degree, like a 90-degree turn, followed by the fracking or the hydraulic fracturing. So hydraulic fracturing is nothing but introducing the millions of gallons of water, sand, and other chemicals to underground to break apart basically the rock and release the gas. So let me briefly talk about the fracking step. So it consists of 3 steps. The first, there's perforation stage where we're going to introduce some small perforation holes, and from which we'll inject the initial fracture pass, and then we'll inject the fracking water basically. And as a result, the fracture will be generated like here. And then during the closure stage, once we stop the pumping, then the water will leak off, and the remaining proppant, or the small particle like the sand, will be trapped by the closing the surface walls, the fracture walls. And if you actually see this, the amount of produced shale gas is determined by the final fracture geometry. And more specifically speaking, it is determined by the Proppant fracture length or geometry, but let me just say it's final fracture geometry. So even a 10% decrease in the length of fracture from the optimal value, say, will result in about 40 to 50% decrease in gas and oil production rate from the shale formation. So this was kind of the theoretical calculations that is done by my colleague Peter Valco at Texas A&M. And I'm not going to talk about the detail, but it's basically saying that 10% decrease will create a lot of issue in terms of the production rate. So then now I want to kind of change my gear toward the shale gas supply chain network. So we've been talking about a lot of production rate or the fracking job and so on and so forth. So basically during the hydraulic fracturing, a huge amount of fresh water is required. And basically, as a result, we need a proper transportation as well as the storage options. And during shale gas production, wastewater, specifically some people call it like produced water or the flowback water, will be collected. And as a result, we need a proper wastewater treatment, storage, and also disposal options. And when the shale gas, and furthermore, the shale gas is the hydrocarbon mixture mainly consisting of a methane. So for a subsequent use, we basically need additional processing units for separation. So therefore, it is very important to consider the shale gas supply chain network at shale gas production. So this is a simple shale gas supply chain network. The upper part is the water network. So as you can see, we'll collect the fresh water. We'll collect the fresh water and then we'll transport them through the truck or pipeline through the on-site. And at the on-site, we'll do the fracking job. And once you have the fracking job, like I said, still there will be like fresh, flowback water. And as a result, they have to be transported to the disposal well or the the facility, like treatment facility. So that's for the water network. And if you look at the shale gas network, we need a processing plant and power plant and all those kind of transportation processes. So if you further look at, and then we can actually decompose it into two parts. First one is a water network, where we need a transportation of fresh water and treatment of wastewater, and also the shale gas network, which will involve a lot of scheduling problem and transportation problem, separating the storing natural gas and natural gas liquid, and from which we can also generate the electricity for selling purpose. So let me talk about a little bit of background. So there has been a lot of work in terms of the feedback control of the hydraulic fracturing. And also there has been a lot of work in terms of the shale gas supply chain network. Specifically, people talk about the fracturing schedule or the environmental impact and uncertainty analysis, and also the water supply network optimization. However, to our best knowledge, there has been no work in terms of combining these two. So for example, if you actually look at the shale gas supply chain network, numerous approaches for the synthesis of shale gas supply chain network, but there has been no work that consider the optimization of a shale gas supply chain by taking into account the optimal fracture geometry, which you can only obtain through the modeling of the fracture propagation with the optimal pumping schedule. Furthermore, from the standpoint of the feedback control for enhanced productivity in shale formations, there's been no work where they consider the economic impact of the actual shale produced from the well. So basically, what we are trying to propose is the following. So first, we'll develop some model predictive control where we're going to use a model, like a fracture propagation model or the reservoir simulator model, to predict how much the fracture will be generated at the end of the pumping. And then with the generated fracture geometry, we're going to use the wastewater model and also the shale gas production model to exactly produce or predict how much shale gas and the water will be generated. And those values will be used within the shale gas supply chain network to optimize the supply chain network configurations. So let me start with the pumping schedule. So for those who actually has been in this field for quite a bit of while, they know that this is one of the benchmark, and a lot of industry, gas and oil companies, they still use something called the Nolte pumping schedule. So this is one of the widely used, and provided we know the efficiency, total pumping time, and pad time, we can predict how much the constant proppant as well as the flow we have to inject to underground. So as you can see, it is actually developed by this simple the formula. So of course it accompanies like a lot of disadvantages. For example, let me just name a few of the limitations. So both practical constraint and proppant settling, are not considered and cannot be considered. And if there's any small plant model mismatch or any small error within the model, it can lead to the premature termination, which is something called the tip screen out, one of the big issue in the operation standpoint. And of course, this is open loop operation, meaning that it does not take any the feedback. So motivated by this, our group initially developed something called the model-based pumping schedule design. So the system was the hydraulic fracturing of the unconventional reservoirs, and the manipulated input which you can actually adjust in real time was the flow rate as well as the concentration at the wellbore. And the real-time measurement that we were able to get from the process was the fracture width at the wellbore and the length of all the fractures with a lot of noise, of course. So the control objective was to achieve the desired average width for each fracture at the end of pumping, subject to constraints and operating conditions. So this is the actual optimization problem we had to solve recursively whenever we have the real-time measurement, and we're going to apply this to the system in a recursive manner. I'm not going to talk about the very detail, but we had some constraints on the flow rates and also the concentration and some material constraint to make sure that we inject the whatever amount of proppant that we want to inject. And also the measurement were given as some input to this optimization problem at every sampling time. So we just talk about the model predictive control from which we, and then once we solve it, and then we can calculate the freshwater requirement as well as the final fracture geometry. And each one of them will be fed to the following two models. First, to the wastewater model. So wastewater model, I mean, we are currently developing some first principle-based wastewater the prediction model to basically describe how much wastewater or the produced water can be collected with time. But I think, as far as I know, there is no such first principle-based model available. So for the purpose of this study, we use actually the EPA, not the model, but EPA data, and we used a simple empirical model. I didn't describe the whole detail to basically predict how much wastewater can be collected once we provide the amount of fresh water. And using, for the purpose of shale gas production, we use something called a CMG. So they developed a reservoir simulator called the CMG IMAX to model the gas production. So once we provide the fracture length, fracture height, or the average fracture width and the number of fracture per well, which is more like the final fracture geometry, we were able to predict how much shale gas can be obtained with time. So I think within this study, we consider the 10 years of time horizon. So once these two data are obtained from the shale gas production model and the wastewater model, we use those two data and then we inject them into the shale gas supply chain networks. So the objective was to maximize the overall profit of this supply chain, shale gas supply chain network, considering the revenues of electricity and natural gas liquid, as well as other costs. So we maximize the overall profit, which is the electricity revenue and the engine revenue minus the other total cost. So other total costs include the freshwater supply, wastewater treatment, shale gas production, processing, and so on and so forth. And as you can see in the bottom, they are actually the function of these three factors. One is the freshwater requirement. Second one is the wastewater recovery ratio. And third one is the shale gas production rate, which we all have from the previously developed the model. So from the supply chain, shale gas supply chain network, we obtained the optimal scheduling of a hydraulic fracturing job, and as well as the optimal shale gas supply chain network configurations. So we basically compared the two cases. One is based on the benchmark, which is Nolte's pumping schedule, and the other one is based on the model predictive control-based pumping schedule, which we developed. So this is actually the pumping schedule, which we obtained from the proposed model predictive control scheme. And as you can see, the flow rate and the concentration varies with time. And then if you look at actually the average fracture width at the end of the pumping, we were able to achieve the set point. And this is a simple comparison of the model predictive control as well as the Nolte's pumping schedule, which is our benchmark. And as you can see, with the proposed model predictive control scheme or the pumping schedule, we were able to achieve the 120 meter. And in this particular case, the 120 meter was the optimal fracture length obtained from the theoretical calculations. So when we compare these two cases from the Nolte's pumping schedule, which is nothing but using that given formula, as a result, when we compare the fresh water required, it required much more fresh water than the model predictive control scheme. And subsequently, and even though they required more water, but they were not able to actually reach the desired fracture geometry. And as a result, the shale gas produced, which is predicted by the CMG program, from the well was much less by the Nolte's pumping schedule compared to the model predictive control scheme. So with this, when we actually compare the shale gas production rate only, the total amount of produced shale gas that utilized the model predictive control-based pumping schedule was about 8% higher than that utilized the Nolte's pumping schedule. And this is the final optimal config, the shale gas supply chain configuration between two. The one was when we used the Nolte's pumping schedule, and the other one is when we used the proposed model predictive control schedule. And as you can see, the only difference kind of is the treatment part, like here, between those two. But other than that, they were pretty much same. And this is a more detailed breakdown of where we actually, using the model predictive control scheme, we were able to outperform the benchmark. And as you can see, we were able to be better in terms of profit and electricity generations, as well as the processing. So the conclusion is that we focus on the development of a new framework to integrate the model predictive control-based pumping schedule of hydraulic fracturing and shale gas supply chain network. So this framework allowed to determine the optimal configuration that actually maximize the overall profit of the shale gas supply chain network by taking into account the final fracture geometry obtained by applying the model predictive control-based pumping schedule. And when we compare this with our benchmark, we achieved the overall profit of 5% higher. So we think this is a very promising the kind of result. So I've been kind of studying a lot in terms of how to develop the optimal pumping schedule by taking into account a lot of models developed from the geophysics people, like petroleum engineering people, and so on and so forth. And then now I'm actually in a discussion with Halliburton and also Schellenberger, because we are using the program developed by the Schellenberger to kind of apply the developed approach to their field. So with this, I want to conclude, and I'm happy to take any questions if you have any.
Thank you, Joseph. And questions from the audience? Happy silence? Yeah, Justin.
What do you think are the challenges in terms of the actual modeling of fractures? Do you think it's fairly faithful to what's happening in reality? I've seen some studies where they've done like mine backs or different tests, and they find that the fracture network is really much more complex than they expected it to be.
Right, so I think the one thing is that rather than, so this is the reason why, so this is kind of the NSF funded project, and then in order to propose them like a fracking problem, because they don't like the fracking because they thought that this is kind of done deal, and then a lot of industry people, they are willing to support it, but so I had to actually propose this like some interesting moving boundary problems, and it, you know, as a result requires a lot of fundamental studies and so on. But when I actually talk to like industry people, there are always two routes. One is data-based people, and the other one is first principle-based. And this is kind of from the insider, but I think that each company has different views. So maybe some companies, I mean, I name a few, but you know, some companies, they kind of not abandoned fully, but somehow putting a lot of their resources on the one side versus the other. So I mean, each one of them has like different view. So I think, but you know, like you said, the machine learning is one of the emerging field, and people want to apply the machine learning rather than using everything in terms of the first principle-based model. So maybe for time being, I think that's what they will do. But maybe if they understand the machine learning is not the kind of Avengers, right? Then I think maybe they will come back to the first principle model, but I'm not sure.
It's a shame that they see it as an either or.
Mm-hmm, mm-hmm.
I think that it can be both.
I mean, it can be both, but then there's another field called the hybrid modeling, right? So, I mean, each one of them has a different pros and cons, but I mean, since I'm not a CEO of this company, so I don't know, but I think, anyway, with all this effort, I think good thing will happen, and the crude oil price will be further go, I don't know, below than what it's supposed to be now. That's my hope, so.
Thanks. That's thanks to our speaker, Dr. Joseph Wang.